Hello friends, here in this video we will see a problem of SFD and BMD, that is shear force diagram and bending moment diagram for a simply supported beam, and for that purpose here we have a question. Draw SFD and BMD for the beam shown in figure below. Here the diagram of the beam is given. For this beam we have to draw the shear force and bending moment diagram. So let us get started. Now here if we see the type of beam, as it is simply supported beam, supported at both the ends. So when the load is acting, here we can see in this diagram a beam AB is supported at A and B, that is simply supported. Next, the length of the beam, which is also called as span, it is 10 meter. At 2 meter distance from left hand support there is 100 kilonewton load acting downward. Then at 4 meter distance from left hand support, that is at point D, there is a couple acting in the clockwise direction. Value is 60 kilonewton meter. Similarly, at point E, that is at a distance of 3 meter from right hand support, a couple is acting of 50 kilonewton meter value. Now, for such a beam we have to draw the shear force and bending moment diagram. Here in this problem, the load is acting downward, so because of that the reaction offered by the supports will be in upward direction. So at A there will be RA, reaction at A. At B it will be R suffix B, that is reaction at B. Now this problem we are going to solve it in 3 simple steps. The first step would be to calculate the values of support reactions. So in the solution part, step number 1, calculation of support reactions. Now here, while calculating the support reactions, I'll use the conditions of equilibrium, and the first condition is summation of Fy is equal to 0, where upward forces are treated positive and downward forces are treated as negative. Here I am not using summation of Fx because there are no horizontal forces on this beam. Now here if we see, RA and RB both are acting upward, so they would be positive. 100 which is acting downward will be treated negative. So I can write this as, therefore RA plus RB minus 100 is equal to 0. So therefore RA plus RB minus 100, when it goes on to the other side it becomes plus 100. So here I will keep this as equation number 1. Next, I use the second condition of equilibrium, that is summation of moment. Now, while calculating moment, either we can take the moment at point A or at point B. If I am taking the moment at A, that is summation of moment of all forces about point A is equal to 0. Here my convention would be clockwise moment as positive and anti-clockwise moment as negative. So therefore, if I am taking the moment at A, I'll get the value of RB. If I see here, RB is acting upward, so when I take the moment at point A, it comes in anti-clockwise direction. So anti-clockwise moment is treated as negative. So minus RB into this total distance, which is 10. So minus RB into 10. Next, here we have 100 kilonewton load, which is the point load. Whenever we are solving the problem, when we want to take the moment, first take the moment of point load and then we can carry forward, we can go ahead with the other kinds of load. Here as I see, there is only one point load, which is 100 kilonewton. It is acting downward, so if I take the moment at point A, it will be producing clockwise moment, that is plus 100 into 2. Then here as I am treating clockwise moments as positive, if we see here at point D and E there are clockwise moment, and they should be treated as positive. So this will be plus 60 plus 50. Is equal to 0. These are the moments which we have. So therefore on calculating this, I'll get the answer of RB as 31 kilonewton. Therefore I'll put this value of RB in equation number 1. So RA will be, therefore reaction at A will be equal to, here we have 100 plus RB. If I send it or to the other side, it becomes minus RB. So 100 minus RB, and RB is 31. So 100 minus 31. So RA value will be 69 kilonewton. So this is the first step where I have calculated the values of support reactions. RA is 69 kilonewton, RB 31 kilonewton. Now here we complete step number 1, that is calculation of support reactions. Now step number 2. Step number 2 is called as shear force or SF calculations. And for SF calculations, see, whenever we are solving the problems on shear force and bending moment, we need to know the sign conventions. In case of shear force also, we need to have the sign convention first. So the convention is here I am taking a section, and even here there is a section. So at first, any force which is acting to the left of the section and upward direction, then if a force is acting to the right of the section and downward direction, both these forces are treated as positive. So I will combine them. They are treated as positive. Next, if to the left of the section there is a downward force, to the right of the section there is upward force. So again I will combine them, and they will be treated as negative. So these are the sign conventions for shear force. Now, if we have a simply supported beam, we should start the shear force calculation from left hand side. That is, we would be using the left hand side as a reference and going on calculating the values. So first I will calculate shear force at point A. So therefore I will write down shear force, that is SF, at point A is equal to, now for that, suppose I am taking the section to the left of point A. Now if I am taking the section to the left of A, there are no forces on the left hand side of this section. So shear force on the left hand side will be 0. But if I take the section to the right of A, that is very close to A on the right hand side, now when I am taking the section, then to the left of this section there is upward force. So as per the convention, upward force to the left of the section will be treated positive. So here the shear force is plus 69 kilonewton. So SF at point A is equal to plus 69 kilonewton. So now we have got the value of shear force at point A, that is equal to plus 69 kilonewton. Next, shear force at point C is equal to. Now in the beam diagram, as we can see, there is no load between A to C. So if there is no load between A to C, shear force value should remain constant between A to C. That is, the value will be 69 kilonewton between A to C, and that will continue up to the left of C, up till here. That is, if I am taking the section to the left of C, it will give me the same value, 69 kilonewton. But if I am taking the section to the right of C, then here I have the section, and to its left there are two forces, 69 kilonewton upward. So to the left of section, upward force is positive, 69 is positive, then 100 is acting downward. So to the left of section, downward force is negative. So this will be plus 69 minus 100. And it gives me the value as minus 31 kilonewton. Next, after this, that is getting the shear force at C. Now, if we see at point D, there is no load at point D. We must be very careful here that at point D, there is only a moment acting. So, if suppose there would have been another point load at D, at that time we would have got shear force value at point D, which would have been different. Now, here the value of shear force at C and shear force at D will remain same, because between C to D there is no load. So whatever, if I am taking the section also to the left of D, it will give me the same value as the shear force at point C. So since there is no load between C to D, the shear force will remain constant. So therefore SF at point D is equal to the same value, minus 31 kilonewton. After this, SF shear force at point E is equal to, now again here at point E also there is no point load acting, or no load is there between, I can say, D to E, C to D, there is no load. So the shear force value which we have at point C, it will continue up to point D and up to point E. So the same value, that will be minus 31 kilonewton. Then at last we reach point B. Now if I am taking the section to the left of B, then here I can see on the right hand side of B there is only one load which is acting upward, that is 31 kilonewton, and to the right of the section upward force is treated as negative. So therefore the shear force at B is minus 31 kilonewton, and this will be the same value because between C, D, E and B there are no loads acting. So whatever shear force value we have at C, that will continue up to point B. Now once we have found out the values of shear force, we can draw the shear force diagram, and for that we need to draw the beam again. That is, here I'll draw that beam again which is given in the problem. Now here I am drawing the beam diagram again. the dimensions also. Now here I project these points one by one. That is, first here, as we can see, I am projecting point B downwards. Next, point E. Then point D. And point A. Now, whenever we are drawing the shear force diagram, it is drawn below the beam diagram. So here there will be the SF diagram, that is shear force. So first we need to draw a horizontal line. This horizontal line indicates 0 kilonewton force, that is the reference line. Now SF at point A, and here I will also write the reactions. At A it was 69 kilonewton, at B 31 kilonewton. Now at point A, the shear force value is plus 69 kilonewton, and while drawing the beam diagram I had explained that if I am taking the section to the left of A, then there are no forces on the left hand side. So shear force value at A, first it is 0. When I am taking the section on the right hand side, then the value is 69. So SF at point A should start from 0 and it should take a positive value. This positive value is plus 69. Here the load which I am showing, that is having value plus 69 kilonewton. Whatever the values, if the shear force is positive, we have to show it above the 0 kilonewton line. If the shear force is negative, we have to show it below the 0 kilonewton line. Now between A to C, this load will remain constant, and when there is no load between the 2 points, shear force diagram is a straight horizontal line, and here the value is plus 69 kilonewton at C also. Then because of this 100 kilonewton at C, the value of shear force changes. So after 69 kilonewton, it becomes minus 31 kilonewton. Since the value is negative, then we have to go below the 0 kilonewton line. And here I'll say that the value is 31 kilonewton negative. And next, this value of minus 31 kilonewton will continue up to D, E and B. So there will be a straight horizontal line throughout because there is no load between C to B. So the SF value will remain constant and it reaches a value of 31 kilonewton, and finally this value will be 0, that is if I am taking the section to the right of B. At the right hand side we don't have any forces. So whatever diagram I have plotted above the line, that is positive, below the line, that is negative, and here with this, here we have to make a small section. And with this we complete the shear force diagram SFD. Here goes the step number 2. So now here we have completed step number 2, that is the shear force diagram. Next, step number 3. It is bending moment. Calculations. So we have seen step number 1, calculation of support reactions. Step number 2, shear force calculations. Step 3, bending moment calculations. Now, see, whenever we have a simply supported beam, then at the supports, that is at point A and point B, the moment will be 0 because there is no part of the beam which is extended beyond A or no part of the beam which is extended beyond B. So the bending moment at A and B will be 0 and we have to start with that. That is, first I'll say that moment at A, m suffix A, moment at B, m suffix B is equal to 0 kilonewton meter, and the reason for this is since it is simply supported, because at A and B the beam is simply supported. Now, as I have shown the sign convention for shear force, in case of bending moment also we have a sign convention. I'll draw that because without the sign convention we cannot move ahead in the problem. Now, here if I have a section, then clockwise moment to the left of section and anti-clockwise moment to the right of section, both are treated as positive, also called as sagging bending moment. So sagging bending moment is taken as positive. Next, if I have a section, to the left of the section there is anti-clockwise moment, and to the right if there is clockwise moment, both of them are treated as negative and it is called as hogging bending moment. So here we see that hogging bending moment is negative, sagging bending moment is positive. Moment at A and B is 0. Next, moment at C means we are calculating the moment here. Whenever we are calculating the moment at a point, we can take either the left hand side of the section or the right hand side of the section for calculating the bending moment. Now, if I see to the point C, to the left of it there is only one force, so the calculation will be very easy here since it is a single force. So when I am taking, now here I have point C, to the left of point C there is RA acting upward and it will be producing a clockwise moment at point C. That is, if I am taking the moment RA 69 into 2, that will be clockwise, and to the left of the section clockwise moment is treated as positive. So therefore moment at C will be equal to plus 69 into 2, and this value comes out to be plus 138 kilonewton meter. So this is the value of moment at C. Now moment at D is equal to, here the point to be remembered is, when we are having a moment which is acting at a point as shown in the figure, at D there is a moment given. So whenever the moment is given, we will get two values of bending moment. First, by taking the section to the left of D, where this bending moment will not come, and the second value will be taking the moment or taking the section to the right of D, where this bending moment value will also come. So first I am calculating the moment at D by taking the section to the left so that this bending moment or this value of moment is not there. So when I am taking this section, we have two forces here. First RA. RA is producing again clockwise moment at point D. So to the left clockwise is positive. So 69 into 4. Then to the left of this section we even have 100 kilonewton and it will be producing anti-clockwise moment at point D. So to the left of the section, anti-clockwise moment is treated negative. So minus 100 into 2. So therefore the moment at D will come out to be 76 or plus 76 kilonewton meter. After this, as I have told, whenever there is a moment acting at a point which is given in the problem, we are going to have two values of bending moment at that point. So first, by taking the section to the left of that point, now I take the section to the right hand side of this point D. So if I am taking the section to the right hand side of this point D, the remaining moment which I have calculated, that is 69 into 4 minus 100 into 2, that gives me the value as plus 76 kilonewton meter. It will remain same, but only thing is, to the left of this section I have to add this moment also. So here if we see, to the left of section there is clockwise moment, and clockwise moment to the left of the section is treated as positive. So moment at D, another value, will be equal to, first of all we have plus 76 as it is. Now in that I will add 60 kilonewton meter, because that is clockwise moment. If suppose at D the moment would have been anti-clockwise, then I would have subtracted it, because to the left of section anti-clockwise is negative. So here I'll get the value as plus 136 kilonewton meter moment at D. Now similarly we have point E at which there is a moment acting. So we will have two values of bending moment. First, taking the section to the left of E, I'll calculate the value of moment. Now when I am taking the section to the left, here I have RA which is 69 kilonewton and it produces clockwise moment. So to the left clockwise is positive, that is 69 into this total value from point A to E. The distance is 7, so plus 69 into 7, then 100 kilonewton. If I am taking the moment at E, it will produce anti-clockwise moment. So minus 100 into 5, then to the left of this section we even have 60 kilonewton meter. So clockwise moment is positive, so plus 60. So therefore the moment at E comes out to be, it is 43 kilonewton meter, which is a positive value. Moment at E. Next we will have another value of moment at E. So moment at E is equal to, this 43 kilonewton will remain as it is, plus 43. Now I take the section to the right of E. So if I am taking the section to the right of E, then on the left hand side we have 50 kilonewton meter, which is clockwise. So to the left clockwise moment is positive, so plus 50. That gives me plus 93 kilonewton meter. So these are the values of bending moment. Next we will be plotting them on the diagram and drawing the bending moment diagram. So now, as I found out the bending moment values at each of the points, the next thing would be to plot these values, and if we see here all the values are positive. So next I'll have to draw the bending moment diagram, and that bending moment diagram will be drawn below this shear force diagram. So at first a horizontal line which shows 0 kilonewton meter as the bending moment, and this line will be the reference for us. Now the bending moment at A is 0, at C the value is plus 138 kilonewton meter. So when the value is positive, we have to plot it above this line. (138 kilonewton meter). Next, at point D we have two values. First, it is plus 76. Here I'll show the value. This is plus 76 kilonewton meter. Next, plus 136. So another value at this point, that is plus 136. Kilonewton meter. Next, at point E, again there are two values. First, plus 43, then plus 93. So plus 43. I'll show it here. Then plus 93. Now, how I would be connecting these points? First of all, the value is at A is 0. So from 0 kilonewton meter, the value of bending moment increases to 138 kilonewton meter, and now as there is no load between A to C, so bending moment will be an inclined line. So here we have to say that when there is no load between 2 points, shear force diagram is a straight horizontal line, bending moment diagram should be an inclined line. So from 0 to plus 138 kilonewton meter. Next, from plus 138 kilonewton meter, it goes up to plus 76 kilonewton meter at point D. So at point D, here this value is plus 76. So again there is no load, so between C to D, so bending moment will be an inclined line. Then from plus 76 kilonewton meter, it increases up to 136 kilonewton meter. 136 kilonewton meter. Then from 136 kilonewton meter, it goes to 43 kilonewton meter, which is positive. So here I have 43 kilonewton meter at point E. So again there will be inclined line from D to E. Plus 43 kilonewton meter. Then it increases up to plus 93 kilonewton meter. Plus 93 kilonewton meter. And then finally the bending moment value at B is 0. So again there is no load between A to B. So bending moment will be an inclined line. And here I will write the values. This was plus 76 kilonewton meter. And here the value is plus 43 kilonewton meter. Now, since I can see this bending moment diagram is drawn above the line, so whatever I have drawn, all the values of bending moment are positive. So this is the bending moment diagram. And as we see here, where in the shear force diagram it was crossing, reaching from positive to negative value, at one location the shear force value becomes 0, that is SF is equal to 0, and where the shear force value is 0, bending moment will be maximum. So here I am getting the maximum bending moment as plus 138 kilonewton meter. So as said in the problem, we have to draw SFD and BMD, shear force diagram and bending moment diagram, for the beam shown in figure. We have completed the SFD and BMD for this beam, and with this we complete the problem.